folks, Bill Armstrong here. Thought I'd put together, and I'll try to do this occasionally, I call it like a weekend preview for some sections that you should be looking at this week for the college algebra class, the online college algebra class. This week coming up, week 5, you should be doing sections 3.1, 3.2, and 3.3. Now this video will not be a substitute for actually reading the sections in the book and looking at the videos in the book. I'm just going to kind of hit some of the highlights, some of the high points, and maybe kind of foreshadow what you should be learning this week. But this is not in substitute of actually, reading the book and looking at the videos as you have hopefully been doing. In section 3.1, it starts off talking about relations and functions, and early in the section you are given the definition of a function. And that definition says something along the lines of a function is a relation that for each element in the domain there is exactly one corresponding element in the range. So it's like, kind of what does that mean? Well, if I draw a blob, I call it a blob diagram, where this first blob will represent the domain and the second blob is the range. This is kind of what that definition is saying on what a function would look like. Let me just pick a few numbers here in the domain, 1, 2, and 3. So a function could send the number 1 over to a corresponding element in the range. Let's just say it sends it to the number 3. 2, that's in the domain, a function could send it to a corresponding element in the range. Let me just make up a number here, 5. And let's say this function happens to send the number 3 to 5 as well. This is a function. It sends to each element in the domain, it sends it to exactly one element over there in the range. Now let's compare that to the following blob diagram. So let me get a blob here, domain, and range. Let's say you saw a picture like this. Say 2 elements in the domain, the numbers 3 and 5. And let's say you saw 3 was being sent over here to the number 1. And let's say that you saw 5 was being sent to the number 2. And you saw 3 from the domain was being sent, try not to cross my ears too much, being sent to the number 3. This schematic represents something that is not a function. And the reason why it is not a function is this one element in the domain was going to 2 different range values. Look at that definition again that's in your book. In order to have a function, this element can only go over to one number in the range. That's why I think in the book it has the words exactly 1 in italics to try to emphasize that. So again, this is a function, this is not a function. So just kind of remember for every number, every element that's in the domain, it's going to go over to just one number in the range, one element in the range. If you have something in the domain that's going to 2 different elements in the range, not a function. So that's kind of what the idea, the concept of what a function is, and kind of give a little meaning to the definition in the book. All right, next up in our study of functions, obviously we're not going to be dealing with these blob diagrams. Most of the functions we're going to be dealing with are actually going to involve variables and an equal sign. So a natural question is, if you are given an equation, how can you tell if the equation, it represents y, the variable y, as a function of x? So given an equation, how can you tell that y really is a function of x? Let's do an example. I'll show you how I can always tell if y represents a function of x. So in this example, I'm just going to do two of them. Say we have a negative 2x squared plus y equals 7. Now let's say we're being asked, for this equation, does y represent a function of x? Well, the answer here is yes, and here's why. I can solve this equation for y very easily by simply adding 2x squared to both sides of the equation. And if I do that, I get y equals 2x squared plus 7. Here's how I know y is represented as a function of x. I have y equals one expression. This is one single expression, 2x squared plus 7. So for this example, in this equation, is y a function of x? The answer is yes. Yes. Y is a function of x. Now let's look at this example. I'm going to pretend it's the same type of question. In the equation, x squared plus y squared equals 9. Is the variable y, is it a function of x? So I'm going to go through the same process that I did here. I'm going to try to solve the equation for y. And it's pretty easy for me to solve this equation for y. I start off by subtracting x squared from both sides of the equation. So I get a y squared equals a 9 minus x squared. And now to finish off solving for y, I have to take the square root of both sides of the equation. Now remember folks, when you actually come in and you do the operation of taking the square root of both sides of an equation, you have to insert that plus or minus. In other words, when I take the square root of both sides, I get y equals plus or minus the square root of 9 minus x squared. In part A, when we solved for y, we had y equals a single expression. Therefore, y was a function of x. Here, I do not have y equals a single expression. I have y equals the positive square root 9 minus x squared, or y equals the negative square root 9 minus x squared. So because I do not have y equals a single expression over here, y is not a function of x. So given an equation, that's how I kind of determine if y is a function of x. I take the equation, I solve it for y. If I have y equals a single expression, it's a function of x. If I have y equals, well, it's not a single expression, then it is not a function of x. All right, hey, next up is function notation. This is notation that will be used throughout the text. If you go on to trigonometry, you'll see it in trigonometry. If you go on to calculus, you'll see this notation in calculus. And this is just purely function notation. Here's what it looks like. You read this as f of x. So that's how I want you, when you see this expression, when you see this, I want you to read it as f of x. Function of x, f of x. And in this, let me tell you a couple of things real quick. In this notation, the variable x, that is the independent variable. Then f of x itself is the dependent variable. Now I'll tell you something here real quick. It's okay for you to think that f of x represents the variable y. That is the dependent variable. So f of x or y, is the dependent variable. Graphically, what's important about all of this graphically is I don't care what the independent variable is. Here I'm saying it is x. But whenever you make a coordinate system, whenever you make a horizontal axis and a vertical axis, you will always label the horizontal axis with the independent variable. And you will always label the vertical axis with the dependent variable. Now, 95% of the time, the horizontal axis is labeled with x. X is the independent variable. And your vertical axis is labeled with the variable y, the dependent variable. So that's a quick look at function notation, independent variable, and dependent variable. All right, hey, now that we've looked at what the function notation is, this is a typical problem, a typical scenario that you'll encounter. Given a function, do some evaluation. So here I'm saying, given f of x equals x squared plus 2, evaluate the following. And the first one we're going to evaluate is f of 2. Okay, here's how basic this is. I'll cut to the chase. If you have f of x equals x squared plus 2, to evaluate f of 2, notice how 2's in the position of x. So wherever you see an x, replace it with a 2. So for f of 2, you're going to put 2 in here for x, and you get 2 squared plus 2. Well, 2 squared is 4. 4 plus 2 is 6. So f of 2 is 6. Quick review here. 2 was the independent variable. 6 is the dependent variable value. So let's say you're asked to evaluate the f of -3. Do the exact same thing. Wherever you see an x, replace it with a -3. So if f of x is x squared plus 2, put -3 in there for x. So you'd have a -3 squared plus 2. -3 squared is 9. So 9 plus 2 is 11. So hopefully you're seeing the process. It's just simply substituting in. So if you see something like this, evaluate the f of w. Don't freak out. Do the exact same process that we did in part A and part B. Wherever we see an x, replace it with a w. So f of w, you put a w in here for x, you get f of w is w squared plus 2. That's it. So to make sure we really understand this evaluation is just a substitution, nothing more, nothing less, let's say you were asked to find the f of Stewie. You're going to do this the same way you did part A and part B and part C. Wherever you see an x, replace it with Stewie. So f of Stewie would be Stewie squared plus 2. It's the concept. You're just replacing. Nothing more, nothing less. So for part E, I'm going to need a little bit more space. So for part E, bear with me while I erase this. So long, Stewie. So part E, you're asked to do the f of x plus h. Do not change the process. It's all about the process. This is the exact same process that we did in part A, part B, part C, and part D. The exact same process. So wherever we see an x, we're going to replace it with x plus h. So f of x plus h is x plus h squared plus 2. It's the same process. Now here we could go a little bit further. If you take x plus h and multiply it by itself, x plus h squared, you'd get an x squared plus a 2xh plus an h squared plus 2. So we could actually simplify that a little bit. The same process though. So let's say part F, we're asked to do the f of x plus h minus f of x all over h. We see something nasty, ugly. Looks horrible, but it's not that bad. By the way, folks, this is called the difference quotient, something that you should read about. It's called the difference quotient, but it's the process. The f of x plus h, well, we just did that in part E. We determined the f of x plus h is this mess. So we'd have f of x plus h is x squared plus a 2xh plus an h squared plus 2. Then it says minus f of x. Well, what's f of x? F of x is just x squared plus 2. So minus, now I should take care to put x squared plus 2 inside parentheses so I don't make a careless sign mistake. So this is the mess we get when we do f of x plus h minus f of x all over h. And you know, we can clean this up just a little. So let me kind of tag it up here. And when I say clean it up, if we distribute the negative 1 here, we get an x squared plus a 2xh plus an h squared plus a 2 minus x squared minus 2 all over h. So that's just distributing the negative. And then you notice once you distribute that negative, look in the numerator, you're going to have some stuff cancel out. The x squareds cancel out, the 2's cancel out. So look at that. You've cleaned it up to a 2xh plus an h squared. Well, that was kind of nice, wasn't it? Oh, all over h. Almost forgot my denominator. So that was kind of nice. Oh, hey, look at this. There's an h up here in the numerator that you could factor out. So why don't we go ahead and factor out that h. And then as long as h doesn't equal 0, you could cancel out the h's and get down to this completely simplified form for the f of x plus h minus f of x over h. So keep in mind, function, when you're evaluating, it's just a substitution. Whether or not you're finding the f of 2, like we did in part A, and you just put a 2 in for the x's, or the f of negative 3, like we did in part B, and you just put negative 3 in for the x, or you're asked to find the f of Stewie, where you put Stewie in for the x, or in part E, the f of x plus h. You're just putting x plus h in there for x. It's just a substitution process. That's all you're doing when you evaluate a function. Okay, the next item that I'll go over here real quickly is the vertical line test. The vertical line test is kind of like the graphical way to look at the definition of a function. So it's if you're given a graph, how you can determine if the graph represents a function. I already showed you the blob diagram, and I showed you if you're given an equation, how you can determine if y is a function of x. So this is kind of like the graphical way. If you're just given a graph, how do you know if y is a function of x? And it's the vertical line test. And I'll just verbalize my version of the vertical line test. I look at a graph. If I can draw one vertical line that intersects the graph in more than one point, it is not a function. So quick example. Let me sketch up 3 graphs here. So look at the graph in part A. Any vertical line that I draw will intersect this graph in only one point. Therefore, this graph represents a function. Look at part B. Any vertical line that I draw here is going to intersect the graph in only one point. So in part B, the graph represents a function. Now look at the graph in part C. All it takes is one vertical line that intersects the graph in more than one point, and it is not a function. Here is a vertical line that intersects the graph in more than one point. It intersects the graph in 2 points. Therefore, the graph in part C is not a function. And that in a nutshell is the vertical line test. All right, the next thing we'll kind of preview is domains. You saw the word domain in the definition of a function. You saw the word domain at the beginning when I did the blob diagram. So here's what I want you to kind of think of in domain. Domain will be the values you're allowed to put in for the independent variable, which most of the time is going to be x, so that nothing bad happens. Now, what do I mean about when I say nothing bad happens? Well, here are bad things in function land. Any value for the independent variable that makes the denominator 0, that's bad. We cannot divide by 0. Any value for the independent variable that will produce a negative number under an even indexed radical, that's bad. We're only talking about functions of real numbers, no imaginary numbers. So that would be bad. And the third bad thing, you'll see later on. I'm not going to tell you right now. It's not coming up in this section or this week. It's coming up in a future chapter. But there is a third bad thing. So for right now, any values for the independent variable that makes the denominator 0, or any values that would make a negative number appear under an even indexed radical, those are bad things in function land. So here are typical directions that you're going to see. It's a typical problem. Determine the domain for a function. So here's the first function. And you're asked, determine the domain of this function. So when you hear determine the domain of a function, you should be thinking, what am I allowed to put in for the independent variable x? What numbers are allowed to go in for x? You don't want anything bad to happen. Well, when I look at this function, I don't think anything bad can happen. I think I can put in any number I want for x, and there's not going to be a problem. I'm not going to end up with 0 in a denominator of a fraction because I don't even see a fraction here. I'm not going to end up with a negative number under an even indexed radical because I don't see a radical here. So nothing bad can happen. Any number I can think of can go in for x. Any number you can think of can go in for x and be cubed, or in for x and be squared. So the domain, I'll just write domain as a D and then make a colon. The domain is any number you can think of. In other words, the domain is all real numbers. Now we write the domain in interval notation, and that's how we would write all real numbers in interval notation, from negative infinity to infinity with parentheses around negative infinity and infinity. So let's look at the next one. Say you're asked to find the domain of the function x over x squared plus a 7x plus 12. All right, hey, it looks like something bad could happen here. I see my function here, I see a fraction. I bet there are some values that could come in for the variable x and would cause a 0 to appear in the denominator. And I can't have that. I cannot divide by 0. No one can divide by 0. So here's what we should do to try to figure out what numbers will make the denominator 0. Let's try to factor that denominator. And I think the denominator factors to x plus 3 times x plus 4. So now when you look at the denominator in its factored form, you should be able to see, well, if x is -3, a -3 in here for x, that would make the entire denominator 0. That's bad. If x is -4, it would make the denominator 0. That too is bad. So I can pick any number I want to go in for x except for -3 and -4. Those are the two excluded values from the domain. So how do I write that down? X can be any real number except -3 and except -4. Well, I'm going to use the interval notation. And here's what it would look like. The domain can be any number up to -4, but I'm not allowed to include -4 because -4 will make the denominator 0. So I put a parenthesis around -4. Union with any number from -4 to -3, but I'm not allowed to include -3. Union with any number from -3 to infinity. So this right here, this interval notation is saying I can put in any number I want as long as I don't put in -4 and I don't put in -3. So that's the domain. Okay, the final one we'll find the domain for is square root 2x plus 1. I think I have to worry here. I suppose I could put in a number for x, independent variable x. I could put in a number that would cause a negative to appear under the radical. For example, if I put -3 in for x, so I toss in -3. 2 times -3 is -6. -6 plus 1 is -5. I would have a negative number, -5, under a square root. That is bad. I don't want a negative number under the square root. So let's think. If I don't want a negative number under the square root, then what I do want under the square root would be positive numbers. Or 0. Well, because 0 is not negative. So that means what's under the radical sign, 2x plus 1, I want it to always be positive or 0. I want it to be greater than or equal to 0. If I solve this little inequality, subtract 1 from both sides, and then divide both sides by 2, I have found my domain. But if I need to write it as an interval notation, the domain is everything from -1/2 to infinity. X is greater than or equal to -1/2. Because I'm allowed to pick -1/2, -1/2 would put a 0 under the square root, and we know the square root of 0 is 0. That's why I have a square bracket here. -1/2 is included. So you're going to do a lot of problems like this, determining domains for functions. All right, as you continue to work through the material this week, we're going to start looking at functions and their graphs. And when it comes time to do some graphs, points that we usually try to find are points called intercepts. The x-intercept and the y-intercept. So let's try just a quick review. Let's say you're asked to find the intercepts for the function 2x squared minus 5x minus 3. So we're being asked to find the y-intercept and the x-intercept or intercepts. So remember, to find the x-intercepts, what you should do is you let y equal 0. Well, y is the same thing as f of x, so to find the x-intercepts, you're letting f of x equal 0. So it gives you this equation. And now you solve this equation, and hopefully it factors. Let's see, a 2x here and x here, minus 3 plus 1. Check it real quick. Yep, that's the correct factorization. And then remember, you set each factor equal to 0. And solve. And these are your x-intercepts. X is negative 1/2, x is 3. So the x-intercepts are technically the points negative 1/2, 0, and 3, 0. But it's the process. Remember, that's how you find x-intercepts. You let y equal 0. And then likewise, to find the y-intercept, that's when you let x equal 0. So here's your function. You're going to let x equal 0, so your y-intercept will be y equals 2 times a 0 squared minus a 5 times 0 minus 3. Y equals negative 3. So the y-intercept is 0, negative 3. So that's a quick refresher on how you find x-intercepts and y-intercepts. Hey folks, next up is going to take a quick look at what your book's going to call relative maximas, relative minimums, and intervals where a function's increasing and where it's decreasing. So here's a graph of some function. I have no idea what the function is. More importantly, I do not care. Think of a relative maximum as being like a hilltop, if you will. So clearly this point right here, it's kind of like at the top of a hill. That would be the relative maximum. Technically speaking, the relative maximum is the actual y-coordinate here. So since this point is at negative 2, 1, the relative maximum is 1. That's the y value. The bottom of a valley, that's where you'll find a relative minimum. Right here, that's a relative minimum. And this is at the point 2, negative 3. Technically speaking, the relative minimum is this actual y value. So here it would be negative 3. That's technically speaking. So think, relative maximum, you're looking at a hilltop. Relative minimum, you're looking for the bottom of a valley. Okay, now where a function is increasing and where it's decreasing. Just think of reading a function, reading its graph like you would read English, going from left to right. So as you look at this graph going from left to right, here it's going up. So this is where it is increasing. Here it's going down. So that is where it is decreasing. And then here it's going up again. So that's where it is increasing. Doesn't look so nice. You get the idea, I hope. When you're going up, you're increasing. When you're going down, you're decreasing. When you're going up, you're increasing. So for this function, I could actually write the following. I'm going to use some shorthand notation. The function is increasing. I could write intervals for where the function is increasing. And the intervals I write are going to be talking about x values, values from the domain. So from negative infinity, starting off way off the board here, negative infinity up to an x value of negative 2. From negative infinity to an x value of negative 2, the function is increasing. So from negative infinity to negative 2, the function is increasing. Also, from an x value of 2 out to an x value of infinity, so from x is 2 out to infinity, it's increasing. So from 2 to infinity, it's increasing. Finally, the function is decreasing from x is negative 2 to x is 2. from an x value of -2 to an x value of 2, the function is going down. It's going down, it's decreasing. So from -2 to 2, it's decreasing. And that's like a quick brief look at relative maximums, relative minimums, where a function's increasing and where it's decreasing. Hey, at this time, the book talks a little bit about even functions and odd functions. Getting chalk dust all over me. In short, here's what the graph of an even function would look like. If you have an even function, the graph is symmetric about the y-axis. An odd function, the graph is going to be symmetric about the origin. So if you're symmetric about the y-axis, it's an even function. If you're symmetric about the origin, it's an odd function. Even function, y-axis symmetry. Odd function, symmetry about the origin. Okay, that's what it looks like graphically. Algebraically, a function is even if when you evaluate f of -x, so when you put -x in for all the x's, you get the original function back at you. Algebraically, a function is an odd function when you toss in a -x, when you evaluate the function at -x, you get the opposite of the original function back at you. So quick recap, graphically, even function has symmetry about the y-axis. Even function, when you evaluate f of -x, you get the original function back at you. Odd function, symmetry about the origin. Algebraically, your function is odd if when you evaluate the function at -x, you get the opposite of the original function back at you. Here, we'll take a look at an example here in a minute. Okay, as promised, some directions that we'll see in the text. You're going to be given a function and you're going to be asked, is the function an even function, an odd function, or neither? So the first one I thought we'd look at is the function 3x to the 4th minus 4x squared plus 2. Folks, here's how I know if this function is an even function, an odd function, or neither. And it's the algebra way of doing it. It's the way that I just showed you. I'm going to evaluate the function at -x. I'm going to evaluate the f of -x. So remember, to determine the f of -x, wherever I see an x, I'm going to replace it with -x. So I'd have 3 times -x to the 4th minus 4 times -x squared plus 2. Now let's simplify this. -x to the 4th power. That's -1x to the 4th power. Well, a negative to an even power will always be positive. So 3 -x to the 4th, that's a 3x to the 4th. -x squared is just x squared. So it's a minus 4x squared plus 2. So check it out. I evaluated the function at -x. This is what I came up with, which was the original function. This is f of x. Since the f of -x gave me the original function, this function in part A is an even function. That's it. That's how I know if a function is an even function, or it's going to be how I know if a function is an odd function, or if it's neither odd, or even, if it's neither one. So, let's do another one. Let's say I'm given this function. F of x equals x to the 7th minus x to the 5th. Okay, I determine if this is an even or odd function the same way I did in part A, the algebraic way. So in other words, I have to evaluate this function at negative x. And when I evaluate at negative x, I just replace the x's with a negative x. And when I take negative 1x to the 7th power, well, negative 1 to the 7th power is negative 1. So negative x to the 7th will be negative x to the 7th minus negative x to the 5th. Well, that's a negative 1x to the 5th. Negative 1 to the 5th power is a negative 1. So negative x to the 5th is a negative x to the 5th. Look how you can simplify this. This is a negative x to the 7th, and then minus a negative is plus x to the 5th. So now look, folks, did we get the same function? No, we didn't. So it's not an even function because we didn't get the same function when we evaluated f of negative x. But what we do have, notice how this f of negative x ended up giving us negative x to the 7th plus x to the 5th. Notice how that is the opposite of this function. If you take the opposite of this function, opposite of x to the 7th, right there it is, opposite of negative minus x to the 5th is a plus. So when you take the opposite of each term here, you get this. This is the opposite of the original function. That means this is an odd function. Here's what all this is building up to. We're not quite there yet on graphing these type of functions. But right now, I'm not worried about graphing this function yet, but I know it's an even function. Because it's an even function, I know the graph of this function will be symmetric about the y-axis. So it's going to be a tool that's going to help us in a future section, like maybe next week. So make sure you know how to do the algebra. Hey, the final thing I'm going to talk about in this preview video, the preview for this upcoming week. In the last section that I asked you to look at this week, the book gives you a lot of graphs. They call them basic graphs. And these are like basic graphs that you should know. And I think I'm going to tell you that I'm just going to tell you the ones I think you should know. And when I say I expect you to know them, I mean know them without using a graphing calculator. Just like if I ask you, right now, what is 6 times 9? You're probably saying, well, 6 times 9 is 54. You didn't need to use your calculator to do 6 times 9. Here are the following graphs that I would like you to know what they look like without having to use a graphing calculator. The first one is f of x equals x, knowing that line. And you'll see these graphs in your book. I'm not going to put them up here. So make sure you know these graphs. The next one is f of x equals x squared. I also expect you to know the graph of f of x equals x cubed. I expect you to know the graph of f of x equals absolute value x. 2 more. I expect you to know the graph of f of x equals square root x. And the last one I expect you to know the graph of is 1 over x. So that's like 6 graphs. I expect you to know what their shape is, what they look like, just like that, without using a calculator. Final thing that I'll look at here is what's called a piecewise defined function. Here's an example of a piecewise defined function. Usually has a brace that looks something like that. And then a rule that's usually broken into at least 2, if not more parts. So it's the function has 2 parts to it. The function is x squared if x happens to be less than or equal to 0. The function is 2x plus 1 if x happens to be greater than 0. Should be a greater than 0. So the function, it has two pieces to it. That's why it's called a piecewise defined function. So you should be able to do some of these old things. For example, you should be able to evaluate the f of negative 2. F of negative 2, well, negative 2, that's a negative number. So you look over here, which one of these rules are you going to use to evaluate the f of negative 2? And it would be this rule. It says use the rule x squared if x is less than or equal to 0. So negative 2 is most definitely less than 0. So you're going to use this rule, that part of the function, that piece of the function, to evaluate. And you evaluate by taking negative 2 and tossing it in there for x. And f of negative 2 is 4. Part B, let's say you're asked to find the f of 0. Well, which one of these two pieces are you going to use to evaluate the f of 0? And again, it will be the top piece. We use the top piece if x is less than or equal to 0. Well, 0 is definitely equal to 0. So we get 0 squared, which is 0. And what if you're asked to find the f of 3? Well, you got to look. The independent variable value is 3. You would use this piece when x is greater than 0. 3 is definitely greater than 0. So this is the piece of the function you're using. This is the rule you're using. So you would toss 3 in for x, get 2 times 3 plus 1, which is 7. So it's just evaluating functions. That's all it is. But knowing which rule to use, it's based on the value of the independent variable. Then if you're asked to do the following, I'll put this right here. Graph this piecewise defined function. Well, knowing the graph of x squared, I said that was one of the graphs I expect you to know. So x squared has a shape like this that you should know, but you're only going to graph the x squared for x less than or equal to 0. So it would be just that part of the graph of x squared that gets graphed. When x is greater than 0, this is the piece you're graphing. Oh, look, we found one point. When x is 3, y is 7. So let's see, 1, 2, 3. 2, 3, 4, 5, 6. Oh, I just fit it on there. So we found one point. I suppose I could find another point. I could put 1 in for x. If I put 1 in for x, 1 is greater than 0. If I put 1 in for x, 2 times 1 is 2. 2 plus 1 is 3. So there's another point. I should know that that's a line. So the graph is a line doing something like this. But I can't technically, when x is 0, I'm using this rule. What number would I get if I put 0 in here for x? Well, let's see. 2 times 0 is 0. 0 plus 1 is 1. Now I can't come down here to 1 and put in a filled-in circle, because that would violate the definition of a function. It would violate the vertical line test. So I have to put an open circle here and boom, do something like that. And that's how I would construct the graph of this piecewise defined function. So to wrap it up, piecewise defined function, you should be able to evaluate, and then I know a couple of problems you're going to be asked to graph the piecewise defined function. So folks, that's kind of like a preview of the week ahead. Feel free to do whatever you want with this video. I know some people have asked for a video like this, and I thought I would try it and see. You can watch it as a preview, so when you're actually learning the material, maybe something that I just babbled, will ring a bell. You could look at it at the end of the week as well. Just let me know if you found it useful. If so, I'll do more. But it does not, this preview video does not replace reading the text, the e-text, and looking at the videos that are in the book. This is meant to be a supplement or a highlight of topics, if you will. But that's it. That's what's coming up in the upcoming week. Thanks for watching.